In this video, we're going to talk about limits for trig functions. I've been saving all these to the end of the limits specific videos. If you don't remember your trig, this may be kind of painful. You really need to remember what the graphs look like. You need to remember your values like sine of pi over 6 and sine of pi over 2 and sine of pi and cosine and cosecant and all the other good stuff. So if you don't know that, you need to do a quick review. I will be putting a very brief review of what this looks like in the comments and the description section at a later date. But if it's not there yet, go find yourself your trig book or your trig notes and kind of go over what they look like. Again, the basic graphs and the basic functional values. Some people learned them in their unit circle. I have a different approach to that, but you still need to know your functional values and specifically your pictures. Now let's talk about limits with trig. Okay, let's do the same things we did before. You should have this list of rules. And the first thing you're going to try is, can I just substitute in the value for x that they're curious about or asking me about? Is it in the function's domain? And if it's in the function's domain, you can just substitute it in there and evaluate the function. Now, if it's not in the function's domain, you're getting 0 in the denominator or something. And in the past, I haven't talked too much about getting 0 over 0 because we're going to do that in a much later video. But if you're getting 0 in the denominator, then you may have to do some playing around with it. But then you would try to see, can I factor it? Can I clean it up? Can I do any number of things to try to get it to some approach that I'm familiar with? But the first thing, and please don't forget this one, is to try to substitute it in. So if you have something that looks like the limit as x approaches pi over 6 of sine of x. I typically on my test try to give a problem, kind of let's get kind of in swing of taking the test, have a fairly straightforward problem. When I do a really straightforward problem on limits, for some reason the students are all trying to do something like, oh, well, let's try to factor it, let's try to do whatever. But, is pi over 6 in the sine function's domain? Now remember, the sine function is not a polynomial, but this is the period of it from 0 to 2 pi that you mostly deal with, but it actually goes on forever, right? Its domain is minus infinity to infinity. So pi over 6 would be in its domain. You just have to substitute it in and evaluate it at that point. So what they're saying is, do you remember what sine of pi over 6 is? Hopefully you do. And the answer is 1/2. Now, if they had said, let's do x approaches pi over 6 from the right, you would still do the same thing, because if this value for x is in the function's domain, coming at it from the right or coming at it from the left is going to get to the same value, because if you're coming into pi over 6 from the left, it's still coming up to that value. And if you're coming in from the right, it still comes to that value. So sometimes teachers, being like we are, we try to fake you out and put a little plus or minus there. But remember, if pi over 6 or whatever value you're talking about is in the function's domain, a one-sided limit is the same value as a two-sided limit. So you just have to put the actual value in there and evaluate it at that point. So you would say this is the limit as x go to pi over 6. And if they had said from the right, you have to put from the right. If you leave it off, you're partially wrong. So let's talk about that for just a second. Some of you may be very frustrated with The fact that you can't just spit an answer out, you have to have the proper format, you have to have a lovely final sentence, you have to put a box or circle it, or your teacher takes off a point here or there, or some teachers will take it all off. So if the teacher says, I am asking you to talk about pi over 6 as you come in from the right, and you leave the plus sign off, even though your answer is right, they'll take off because your answer, the value is right, but the whole statement is not 100% correct because I didn't ask you about the two-sided, I asked you about the one-sided. Now, why is that? So that doesn't hardly seem fair, but it actually is, because if you're in calculus, you're going into a field, I've mentioned this before, where communication is key. You may or may not take another calculus course, but you probably are. But your job, whether it's some sort of medical thing or engineering thing or physics thing or whatever, requires you to have to convey information to someone else. And close is really not good enough. And so if you sort of kind of maybe give them the answer and the answer's right, but it's said in a confusing way, not exactly answering the question they have, they're going to get all sorts of confused and possibly hurt themselves or hurt others. So you have to pay attention to the details. That's part of this course. This course is not just teaching you how to find an answer. This course is teaching you how to be precise with your answers and how to be precise with explanations for how you got that answer. Let's try another one. So let's say, what's the limit as x goes to pi over 4 from the left of the tangent function? And we need to do a little bit of talking, as if I haven't been doing that. Okay, so let's talk about the tangent function. And the tangent function, if you remember it, looks kind of like this. Almost looks like your cubic. And it had asymptotes on each side of it. It was not continuous, like sine and cosine. But it repeated itself. And if you remember its period is pi, right? Right? Not 2 pi. So this is pi over 2 on this side and pi over 2 on this side. It's a minus. Okay? So again, if I'm saying what is tangent doing as you approach pi over 4 from the left? Okay? Pi over 4 is here in the middle. For this portion of tangent, it is continuous within this portion. So pi over 4's value up here, tangent of pi over 4 is 1. So whether you're coming in from the left or whether you're coming in from the right within this interval right here, it's like it's continuous. So the answer is 1. Okay. Now, some of your teachers will take a picture as justification for something. Some of them are going to want you to work through the math, but for this particular problem, since you're supposed to have memorized that the tangent of pi over 4 is 1 from somewhere in your previous life, you can just write down 1. The picture may or may not help you. We're going to use that picture for the next part. However, if they said, what's the limit as x approaches pi over 2, it's supposed to be tangent, from the right, okay, you go, wait, tangent of pi over 2. Oh yeah, tangent of pi over 2 is undefined, right? Because you're right here at this asymptote. And if it's undefined, you cannot just substitute the number in, right? Okay. So if you remember your picture, right, as you're coming into pi over 2 from the right, the tangent function is falling down like this. And so the answer would be negative infinity because it's going down to negative infinity. Now, for some teachers, and I'm one of them, the picture would be sufficient. So if you showed me the picture and kind of went, okay, we're doing negative infinity, and you either circled this part of the picture or, circled both of these, and somehow let me know that you're using this figure, to justify that answer, I I actually like the idea about the picture because that says to me you are bringing forward your trig, you remember your trig, you remember how it's going, and I would go for that. Some teachers, okay, what they're wanting for tangent is they may want something more like a numerical approach. So you would say, okay, how about we do this? And tangent is sine over cosine, correct? All right. Now, I'm going to draw the figure, even though if they didn't like this other figure, they won't like this one, but this might help you to remember what's going on. Okay, so sine looks like this. Okay, cosine looks like this. Okay, now as you're approaching pi over 2, now this is pi over 2, and this is sine, and this is cosine, and here's pi, and here is pi over 2, just so you can kind of get a reference. Let's talk about what's going on, all right? So as sine gets closer to pi over 2 from the right, it's coming up like this. So sine is climbing as you get closer to pi over 2, and it's getting close to 1, right? It's kind of getting close to 1, right? But cosine, as you're coming in from the right, is climbing like this. It's getting closer to 0, but it's negative values, right? It's negative values for y as you get closer to 0. So it's a negative tiny number. And if your teacher gets like almost ill when you say tiny number, you can make one up. So it's basically close to 1 over something like, or if they get cranky about that, you could say it's like 0.99 over negative 0.01 or something like that, okay? But at any rate, any positive number divided by a tiny negative number, right, is going to be negative infinity, okay? You need to find out from your teacher, and usually they're demonstrating this for you, and what they demonstrate in the class is what you need to give them back. But if it's an online course and you're not real sure, and they just say go out and look for a video somewhere, and you're going to take the test online, and they just need an answer, I would draw the picture, okay? But you need to identify from your teacher what they want, because if your teacher does not let you use the figures, this figure right here, and you have the correct answer right here, your teacher will say, you have not justified your answer. I don't care that that's the right answer. You didn't justify it. Or if you just imagine what the figure looked like and this one was not here, and you're imagining it in your head, or you put it on a different piece of paper, they're going to go, well, you probably had a 50-50 shot. Was it positive infinity or negative infinity? I don't give you full credit for guessing because you didn't justify it. So calculus is all about justifying your stuff. Okay, so let's do another one. Let's do the limit as x goes to pi of the cotangent. Y'all might not can read my writing. Cotangent of x. So let's go back to the figure. Sometimes students take tangent. Okay, here's tangent. And they say that since tangent looks like this, cotangent is its reciprocal, and they know that for reciprocals you flip them upside down like this, so they try to make cotangent look like this, and that is absolutely not right. So I always put a cotangent problem on the test so that I can fix that misconception. Okay, so let's talk about why that's not right. Right here, tangent of 0 is 0. Okay? Now, if you take 0, and you can put anything over 1, if you take 0 and flip it upside down, 1 over 0 is undefined. It is not 0, so you can't just flip cotangent like that. It's not 0, it doesn't go through 0. 1 over 0 is undefined, so when you take the reciprocal of it, there's a lovely asymptote here. And tangent's period is pi, so is cotangent. So cotangent's first, well, the main period that everybody talks about is between 0 and pi. Okay, so it goes like this. And this is pi over 2. Okay, so going back over to here. Okay, cotangent, you have to remember what it looks like. And, I tell my students up front about how, the things that I think they need to remember and how you need to know this for the test. Um, these are things to watch out for. So I am just passing along what I'm saying. You may not have a teacher that's um, focused on trying to get you to remember your trig. Not that I'm drawing it very well today. Okay, so if you remember these things, just repeat. All right, but all we want to know is pi, and here's pi right here. This is actually pretty pathetic. All right, that's a little better. Okay, so if you look at it, all right, then this is a two-sided limit, but pi is not in cotangent's domain. So you cannot just substitute it in. You're going to have to discuss what happens coming in from the right and what happens coming in from the left. Okay, so coming in from the right, here's pi, and you're coming in from the right, then cotangent is increasing without bound, and you're going off to positive infinity. As you're coming from the left, cotangent is dropping and it's negative infinity. So from the right, it's positive infinity, and from the left, it's negative infinity. This does not exist. Now, I'm going to tell you something right now. Okay. I would deal with the fact that your answer right here, your answer is above your justification. Okay? So the work that you're doing to justify does not exist is below where you gave me your final answer. And I would live with that. I know teachers who will count the whole thing wrong because they're like, okay, this is not in any sort of order. And you should know that before you get to the first test, what they're like. So if that's what they are like, okay, you just be sure that you write it down again. And be sure that you get everything in there. And put your answer down here. Okay? You can do this. All right? If they had wanted like a numerical justification, you could have done something like the limit x goes to pi from the left of cotangent x and talked about tangent of 1 over tangent x. And so as you come in from the left, you would say, okay, this is 1 over a tiny negative number, because they would live with that because you know what the tangent original function looks like, and you know what the numbers are that are coming closer to it, and you could say this is negative infinity. So this is kind of more of a number-based approach. This is a figure-based approach. If you're going to go in, if you're not sure, and you're going to go ask your teacher if it's okay, do not go up to your teacher necessarily with a blank piece of paper and say, I have a question for you, and then start going through this. Okay, if I'm going to do the limit of cotangent of x, and then start drawing this figure and everything, because then they have to stand there and wait on you to draw the figure. And if they hadn't considered that question before, they're kind of predisposed to go, No, because they don't want to have to figure this out and wonder what you're doing. And it just seems like, okay, what's going on? If you go up there with this, kind of basically filled in, where you have your figure sketched and you have your potential question here. I think this was what it was. And you say, if I have this situation going on like this, would you accept the figure? Maybe if I circle pieces of it, would you accept the figure as a justification for my answer? And if you already have it there and they just have to say yes or no, they'll probably they probably, or they'd be more likely to say yes. Let me rephrase that. Okay, let's do another one. I tell my students flat out, and I'm not the only one that does this, but I may be the only one who's so upfront about the things to do. Um, because I'm not trying to get you to fail. I'm trying to get you to remember all this stuff. Okay. So this is supposed to be tangent. I'm trying not to write cursive. If you're wondering what it is, I'm trying not to do. All right. So here we go. So if you see something like this and you're going, oh, great. Okay. And then you go, well, let's do my thing. Okay, we're going to do what we're supposed to do. We're going to try to substitute it in. Cosine's domain is negative infinity to infinity. It will take anything you want to put in there. Tangent has issues, okay, where its asymptotes are. And when you look at it, you go, oh, tangent has an asymptote at pi over 2, so, and it's just from the right. So I'm just going to have to kind of sneak up on it and start doing positives and negative little tiny numbers or big numbers or whatever's going on that you're going to do. And then maybe your teacher will let you use a figure to draw this, and then you've got to work whatever's going on with here with whatever's going on there. Okay, but let me show you something. If your teacher gives you a trig limit, and if there's two trig functions in there that are kind of sort of related, okay, so like this tangent and cosine, tangent is sine over cosine. It has a relationship with the cosine over there. You might want to see if you can kind of clean it up first. Okay, so if you have pi over 2 plus tangent is sine x over cosine x times cosine x, and these cancel. So this is just like factoring and reducing. And so literally all I have to do is say, what is sine x doing as I get closer and closer to pi over 2? Well, sine x is continuous, right? Its domain is minus infinity to infinity. So I can just substitute pi over 2 in there. And sine of pi over 2, do you remember what it is? Sine of pi over 2 is 1. All right. So you would say the limit. Now you can't say the limit of pi over 2 of sine x because that's not what they asked. Tangent x cosine x is 1. Um, Sometimes I do things like this. And I'll watch students, kind of work their way through here. But y'all, cosine squared of anything plus sine squared of the same thing is 1. So this is saying what's the limit as x goes to 0 of 1? 1. Okay, because right, because this is your function. So this is actually the function y is equal to 1. And if you graph it, this is y is equal to 1. So what is y doing as you get closer and closer to 0? Y is just 1. That's all it ever does. So this is 1. So if you just have one trig function, you're probably okay with just getting started and looking to see if it's in the domain. But if you have more than one trig function, you might want to see if it cleans up. Okay. So what if you have, this is just another one. I'm just going to set this one up for you. Now, what's the relationship between cosecant and sine? They're inverses of each other. So this is 1 over sine times, and this little square right there is saying the whole thing is squared. It's shorthand for sine x squared, and this cancels one of those. So it's the limit as x goes to pi from the right of sine x. Remember, sine and cosine are continuous, and so you can evaluate it at any x value. So what is sine of pi? It's 0. It takes me more time to write down the problem than it takes to do it. Okay. Now, there really isn't any big deal about whether you put parentheses or not around the x's. Sometimes it looks worse and sometimes it looks better, depending on how messy your writing is. Old style, they used to put parentheses around these all the time. Now they sort of just drop them off. But it kills me if they go sine of x plus 1, and I'm like, is it sine of x or sine of x plus 1? That makes a difference. Okay. Now, in your calculus book, they have a couple of variations. They're not the old trig identities that you learned back in trig class. These are some that are based on the squeeze theorem, which is in your book, and a little bit of geometry use in the squeeze theorem. And they come up with these very often used things that you just have to memorize. And they're identities. And so we're going to work a few problems on this. Okay, now this is my version of a theta. Okay, notice that the limit, this part with sine theta over theta is equal to 1 is only true if your limit is being taken as you approach 0. So if you're approaching pi over 2 or pi over 6 or 2 pi or whatever, if you're not approaching 0, don't apply these. Now, technically 2 pi is just a multiple of 0, but you get what I'm saying. All right. And so likewise over here, right? Now, the other thing you have to notice is what this is saying is this angle that sine applies to and this angle here have to be exactly the same. So if this is a 2x, this has to be a 2x. If this is a 4t, this has to be a 4t. Okay? They have to match in order for this to be 1. Likewise, this angle right here and this one right here have to be the same. If this is a, I don't know, 5 theta, this has to be a 5 theta. Okay? If this is theta plus 1, this would have to be theta plus 1. Same as over here. Okay? Then your job is just to try to get it into that form. And so it becomes a puzzle. And these are actually kind of fun. Well, you may not think so. I think they're kind of fun. Okay, so I've done worse things. So have you. Think of story problems. You've done worse things. All right. Okay. Everything's relative. All right. Now, so I'm asked this limit question, and you look at this problem and you go, man, if that was just a 3x on the bottom, this answer would be 1 and I could be done. And you don't have to draw a picture. You don't have to sneak up on it. You don't have to do anything like that. If you don't like these, go look at your book about how they explain this. Um, but you just have to live with it. So you're going, now remember, you have a fraction and you are entitled to multiply the top and bottom by anything you want as long as you do the same thing. So you go, I really need a 3 in the bottom. If I was just multiplying by a 3 down here at the bottom, I'd have my 3x and I would be good. Well, I have to multiply by 3 in the top in order to be legal. So in effect, what you have is the limit as x goes to 0. And this 3 does not multiply inside the 3x. Argument of your angle is out here. So it's 3 sine 3x. You can't multiply inside an angle. And down on the bottom, you now have 3x. And now you have this match between here and here. So all of this goes to 1. And you have 3 times 1, which is 3. And you're done, except for your lovely, complete sentence. Okay, let's work this problem that goes the limit as theta goes to 0 of the tangent of 6 theta over sine of 2 theta. And we can think of this because sine of 2 theta is 2 times 0, which is 0. Sine of 0 is 0. Okay, but we're getting close to 0. Now, let's see what's going on, though we can't just say it's going to be a little tiny number and see if it goes off to infinity. There's a lot of moving parts here in the trig world. So this is sine of 6 theta over cosine of 6 theta times 1 over sine of 2 theta. And I'm going to try to work with you on this pattern of how to we're going to make each one of these sines fall into that pattern of sine theta over theta. Okay, so let's do the sine of 6 theta. And what it would need if it were going to try for that pattern is 6 theta on the bottom. So we'd have to multiply by 6 theta on the top. Then we have 1 over cosine of 6 theta. And cosine of 6 theta, if theta is 0, then cosine of 0 is 1. So we're good with that one. Don't have to do anything with that. And we have 1 over sine of 2 theta. And this is going to be multiplied by, we want 2 theta up here over 2 theta here. Now, we actually don't need all of these thetas. If you try this again, you can probably get it done a little bit less multiplying, but I'm going to leave that up to you to try. But I'm just showing you kind of the long way to do it so that you get used to how to make this pattern work. I should have made these red since they're new. Okay, now these two go together, okay, and these two go together. So what you have, and you can, there's steps you can probably leave out. It depends on your teacher. But if you just write the answer down, it's 100% wrong. So you have this 6 theta still left, okay, times 1 over cosine 6 theta. And you have 2 theta over sine of 2 theta here. And I'm going to take this 2 theta and drag it back over here with these other red ones, so you'd have over 2 theta here. So I'm bringing this 2 theta back over, okay? And 6 theta over 2 theta is just 6 over 2, right? I'll reduce that later in just a minute. But these thetas are going to cancel out, okay? Now, according to this definition of this trig based on the squeeze theorem, as I go off to 0, sine of 6 over 6 theta goes to 1, okay? This 2 theta over sine of 2 theta goes to 1. So what I've got is the limit as theta goes to 0 of 1 times 6 over 2. Yes, you can cancel whatever you want, but I'm trying to walk this really slow in case you're confused. 1 over, now, this is cosine of 0 because 6 times 0 is 0. Cosine of 0 is 1, okay, times 1. This is really clunky looking, okay, but I'm trying to show you where all of these came from, right? And as you clean this up, since you're actually doing the limit to 0 as you're going through here, you probably don't, well, you don't actually need this limit, but if you put an extra one in there, usually teachers don't care. And so what you have now is all these ones, and 6 over 2 is 3. So this turns out to be not something that looks like it's going off to infinity. It looks like this. Now, sometimes students get used to these concepts. They've done a few, they see some in the class, they do a few on homework, and they go, you know what I've noticed is that, a lot of times this sort of ratio of parts right here, it's either that ratio or sometimes, depending on what's going on, it's the reciprocal of that ratio. And you start thinking that, this is a 100% always going to be the answer type thing. Okay, even if your answer's right, which 6/2 is 3, if you didn't do this work, and the next line and what you do is you take the statement that the teacher gave you and you go, oh, the answer's 3. There you go, beginning and the end. I don't show any of this. And you just tell, even if your answer is correct, it's going to be marked wrong because you didn't justify your answer. It is not enough to have the right answer. You have to justify how you got there so that the reader can follow along with the explanation. Now, that's the sad part about online classes is that if you take your test online, you don't learn that. Okay, you don't learn the importance of the justification. So if you have a teacher who's picking up your tests and grading them, you thank them and say, I'm so grateful that you are providing me feedback. Okay, because that's what originally is for. But goodness, you have to um, provide justification and background for the answer. Do not just throw that answer out there. They have every justification for counting it wrong if you don't explain it, especially if they've, like I do, show all work. Okay, it's just like, okay, all right. So theta goes to 0. So this is one that this 1 minus cosine, you get kind of used to that from that other one. Way back up here. Did I pass it by? No, there it is. Okay, this one right here. The limit as theta goes to 0 of 1 minus cosine theta over theta is 0. Because it zeroes out, sometimes they don't spend a lot of time on this because it's not very interesting. All right, so you cannot just substitute in the 0. That should be the thing you try first because even though sine is continuous and 0 is in its domain, when you put this in here, you'll get 0 in the denominator. You're actually going to get 0 in the numerator as well. All right, but we're going to talk about that case when you get 0 over 0 in a much later video, and I'm just not going to bring that up. But you may see your teacher going, okay, this is 0 over 0, where I just talk about 0 in the bottom. All right, now, so I'm thinking, man, I just need, because this is 1 minus cosine theta here, I just need a theta down here. So I can multiply the top by theta. And then you have sine theta under 1. And you can multiply it by theta over theta. Now, all right, eventually, I'm trying to figure out how to do this, this theta and this, let me do it this way. This theta and this theta are going to end up canceling each other out. So you think, well, why can't I just throw this theta in here then and this theta in there? Um, if your teacher will follow that logic and if you don't make a mistake, I guess you could do that. Okay. But if you're wanting to follow through with the principle of the identity, I'm trying to teach you how to do that. Can you do it in a kind of, okay, I've noticed a pattern kind of way if you apply the pattern correctly, but I'm not going to teach you that. Okay. So if you're sitting there wondering if I have to do that, do I have to really do this with the two thetas? I don't guess you actually really have to, but it saves you from making some errors. So when you do this, what you're looking for is this 1 minus cosine theta pairing with your extra theta left over, this one. Okay, then this pair, make another pattern. And what's left over here is this 1 over theta. So see, when you pull these together, you've got 1 minus cosine theta over theta. Pull this one over to here, or pull the other one the other way. You get theta over theta, theta over sine theta. Okay, doing okay? So this cancels out. And when you put theta going to 0 here, 1 minus cosine theta over theta is 0. Theta over sine theta is 1, and 0 times 1 is 0. But I'm trying to reinforce, the proper presentation and the fact that if you do the presentation and you follow through the steps, and if you don't throw your answers everywhere on your homework paper, your brain will start to work like this. Students laugh at me when I first have them in the beginning of the semester. I'm going, watch, just watch. And by the end of the semester, their brain's like this, and they cannot bring themselves to go any other way than straight down the page. And I just laugh. I said, you've crossed over to the dark side. Okay, now, here we go. Let's try the limit as x goes to 0 of sine of minus 3x over sine of 4x. And so you're not going to do some sort of trig reduction or anything else like this. What you're going to do is go, all right, I'm going to treat these as if they're two kind of separate problems I have to solve. So I have sine of minus 3x over 1. And I'm really looking for that pattern where I have a minus 3x here. So I need to multiply by minus 3x here. And then I have 1 over sine of 4x. And I really want that pattern of having the matching argument up here. So I have to multiply down here. So this sine of minus 3x and this minus 3x make that pattern. And this fulfills that pattern. So I'm going to show you the pattern so it's not quite so messy. And you've got sine of minus 3x over minus 3x. And then you have the minus 3x that's hanging out right here. And I'm going to bring this 4x that's left over there. And then I have 4x over sine of 4x. So this follows that pattern where the argument and this down here match. So this is 1. This is 1. These x's cancel. And it's minus 3/4. Now again, you may have looked at that and went, I bet it's minus 3/4. And if you wrote that down without any explanation on my test paper and none of this was here and you went, oh, this is 3/4, I would go minus 10 or whatever it was that because you can't do that. You have to justify it. Okay, one more and then we're done. The limit as theta goes to 0 of cosine t minus cosine squared t. Now see how that looks weird when you're trying with no parentheses over t. And you're going, well, that's pretty close, right? But not quite. But I can factor out that cosine, one of the cosine t's. Oh, well, it would help if we had the same thing. So these are t's and this is theta. Let's make this be a t. They have to match. So let's make this be a t. All right. So if we factor out a cosine t, that would leave you 1 minus cosine t, because this is a square, over t. So this one is that pattern, right? And if you put t as 0 in right there, you would have this one is going to go to 0. And this part right here is actually 1 minus cosine of 0, which is 1 minus 1, which is also 0. So you've got 0 times 0. So this is 0. So this is the end of this video. I cannot emphasize enough that you need to watch what your teacher does in class, and you need to see how they explain things, their layout on the board. If you've been turning in homework and they've been actually grading it, that also is a blessing. And so the feedback should tell you how well you're doing. But if they're being very sequential and very linear on the board, you cannot just splat stuff anywhere you want to on the paper and expect them to find the answer. Okay, if I have to hunt for the answer, I'm not doing it. And if you give me 2 or 3 answers, I'm going to pick the wrong one. Now, if you have 2 or 3 false starts and you're going, okay, that's a false start, and you go, that's a bad idea. Don't erase it. I don't care that you erase it, your teacher might, but I didn't care if you erase it. Just mark it out and keep going. Okay. But don't give me 3 choices and box in 3 things and ask me to figure out which one it is. Okay. That's just like, no, it's not my job. All right. So, y'all, calculus. It's supposed to fine tune your presentation. It's supposed to fine tune the way you can walk through a series of steps. Now, you have learned, if you looked at the previous videos, a lot of different ways to try to find the behavior, the limits of some sort of function. In the next video, and the link to it's going to be down in the description, the next video is going to be an overall review where I mix them all up and I really quickly go through and talk to you about how you have to do it. In order for you to be comfortable with the next one, you need to have gone through the steps and be comfortable with, okay, the first thing I'm going to do is try to substitute it in. Then I'm going to try to factor it, reduce it. If it has a square root, I might try multiplying by its conjugate. If it's a complex fraction, I'm going to multiply by the least common denominator. If it's not something that I can seem to get into another format, then I may have to use a numerical approach where I use progressively closer numbers, or what I call the sneak up on it method. And if it's a trig thing, first thing I'm going to do is look to see if I can simplify it using some sort of trig identity. And then I'm going to ask my teacher if I can use a figure to justify my answer. And then I'm just going to practice a lot of my trig. So the next video is going to be an overall review. And then in it will be a practice test where I've mixed up a whole bunch of these. And then you can take a practice test and I will actually work out the solutions so that you can, so you should work it like a test and then see if your answer's right, and if not, where your solution and my solution diverge. So I will see you at the review.